So, today we are finally going to define Turing machines formally, and we're going to actually start, in that sense, doing some real math. Before we start, I wanted to mention that, like, if you've never seen any set theory before, you have no exposure to it, I've linked in the video description a PDF that I wrote for one of my probability classes, which is just kind of a crash course intro. It's about 20 pages long. It'll take you a few hours to go through, but if you've never seen any of it, I recommend you go through it. It's got exercises in it for you to do. It's nothing very difficult. It shouldn't be difficult for anybody. It shouldn't be hard or frustrating. But I'm going to assume that you know the things that are in it. Just basic set theory stuff, containment, membership, you know, unions, intersections, all that stuff. It also explains functions, kind of in both the engineering sense as like a black box that does something, and in the math sense of um, uh, being essentially a set or being a relation. So look through that if you are interested in following this and have never seen any set theory before. So we started to describe what we had in mind for a model of computation in the last video, for our Turing model of computation. It wasn't based on the idea it wasn't based on anything that we knew about how a computer worked. It was more based on how people think. And so we had this kind of idea in mind. We were starting to break down the process of somebody thinking at a desk with a piece of paper and a pencil. And the breakdown was sort of something like this. And this is sort of, so we're going to begin with this kind of informal modeling of human thought. And then we're going to formalize that gradually into a mathematical definition. But the informal model of our thinking is that basically at any one moment, at any one discrete moment in time, we are focusing on a particular point in the page, maybe right here, and we have a state of mind. There's something going on in our head. We have our pencil right here, and so there's two fundamental defining features of the current situation. Is that I'm looking somewhere on the page. It's not really the location of where I'm looking that matters. It's what I'm seeing, right? I'm seeing something specific on the page. There's something going on in my head, and I'm going to react to that based on what I see and based on what's in my head. My state of mind is going to change. So the thing in my head is I'm going to change my state of mind. I'm going to change what's at the point that I'm looking at on the page. The response. That's the internal, or sorry, that's the external response. So the internal response is the new state of mind. The external response is I'm going to change, maybe not, the place on the page that I'm looking, and then I'm going to move my attention somewhere else. And then the process is going to repeat itself. Now I'm going to be looking maybe over here. Actually, um, let me pause the video. I think I've just remembered that it's not recording my cursor, and I'm using my cursor to point at things. Okay, you should be able to see my cursor now. So effectively, once my state, so I'm looking somewhere, I have a state of mind, and then based on those two things, based on what I'm seeing, not where I'm looking, but what I'm seeing, that's going to end up being important. My state of mind is going to change. I'm going to use my pencil to change what I see, and then I'm going to change where I'm looking, and I'll maybe be looking somewhere else. So maybe at that point I'll be looking over here, and my state of mind will be different, and then the process will repeat itself, and then it'll just go like that. That's the loop, and we'll have to add a marker kind of informally to say when I'm done. It's sort of uh, that'll have to be defined, but that's the idea. That's the model for human thought. And what we're going to do is we're going to formalize this. And you can see I already sort of started the process by turning the paper that we're looking at into graph paper. Okay, so what I want to start with is the process of formalization of this informal model is going to be, first of all, we need to make some assumptions in order to mechanize what I just finished describing. So I'm going to say this is a fundamental assumptions toward mechanization. We want to make this process feel mechanical enough that we can mathematize it. Okay, so the first assumption I'm going to make is what I already sort of drew, is that the paper is graph paper. I'll make this a bulleted list. Paper is graph paper. And the reason I want to do that is sort of obvious, right? I want to be able to tell, it has to do with where my visual attention is focused and where it's going to change. If I have graph paper, then I can be precise about saying where I'm looking, and I can also be precise about saying where I move, where my visual attention moves. It moves here specifically. There's no in between here and here. Um, and that's fine. I think everybody intuitively will understand that that's fine. That doesn't really lose me anything because if you just look at this curve I drew here, you'll know very clear. Everyone knows this is not actually a curve, right? This screen that you're looking at is a pixelized grid. It is graph paper that you're looking at. It's just so fine. The squares are so small that it looks like a curve. So just in that kind of based on that intuition, I think it should be clear that you're not really losing anything by sort of discretizing the paper. You're just whoops. So that's our first assumption. And that's what that should give you a feel of what I'm going to be doing here in terms of what we're trying to do in terms of mechanizing, what I mean by the word mechanization. The next assumption is has to do with this picture I drew over here. How much graph paper do we have? Well, we're going to assume that we have as much as we want. So graph paper extends infinitely, left and right, left or right. So as you can see here, this is kind of the picture to visualize, right? We just have, I can just keep moving. I have infinite paper, but even beyond that, we want to be a little more precise. What do I mean by having as much paper as we want? It means I have one infinitely long strip of paper. That's kind of what it means. So this is the picture I had. You can kind of think about it as like, construction paper that gets wheeled out like this. Um, when I say infinitely left, right, uh, I want to add the caveat. We're going to say some various things. Usually both. Usually both ways. Uh, but it doesn't really matter. As we'll, one of the things we'll prove is that we just need it to be infinitely in one direction. But the standard model I think usually ends up being that the graph paper goes infinitely in both directions. But more importantly, or just as importantly, is that it's going to be finite though in terms of not infinite in the up down, right? So we only have a certain number of rows on the graph paper. We have infinitely many columns, but we only have a certain number of rows, and that's just to kind of simplify what we mean by infinite. We still have as much paper as we want. We still have as much room for writing things down as we want. So there's no reason to give ourselves infinite rows. It's going to be simpler of a model to not do that, and we aren't losing anything. So it's not infinite in the up down. We're going to prove that the number of rows really doesn't change very much. But so finite number of rows. Usually the number of rows will be 1. So for the standard model, maybe I'll write that here. Um, usually just 1 row. And so, at that point, it's barely even graph paper. At that point, this is why you might be surprised that I say the word graph paper. The word that you usually hear when you're talking about Turing machines is tape, right? If you only have a single row of graph paper, it barely looks like, instead of having a graph paper at all, what we kind of have now is this like strip that goes infinitely in both directions, sometimes just one direction, and then we have a bunch of cells that have things in them. But it is but we got here from kind of starting with this idea of graph paper. And you can give yourself extra rows. It's often useful when you're designing Turing machines to accomplish specific things to have an extra row or two. But even then, since we sort of lost at that point the idea that we have graph paper, usually people draw multiple strips of tape that are disconnected, and then you lose all manner of having it be graph paper in the first place. But the bottom line is that you only have finitely many rows, usually 1, and at that point, it stops being graph paper, sort of. Um, Other assumptions. What just happened? Other assumptions. I said visual attention is focused somewhere. Well, where? How, what it would, can my visual attention be the whole page? Can my visual attention be 4 cells at once? No. We're going to standardize things by um, saying that visual attention is focused on a single cell, one cell at a time. So at any one point, my visual attention is just a single one of these guys. Whoops, no. Just a single one of these guys. What else? Um, Visual attention can only move. So now let's think about my visual attention after one step is going to move elsewhere. But we're going to say to simplify things or to mechanize the process, and this will also help us when we're talking about space complexity later, is that visual attention in one step can only move to an adjacent cell. How do I say that? Visual attention on next step. Well, let me say it like this. Visual attention can only move one cell at a time. So it's focused on one cell at a time, and then in the next step, I'm guaranteed to be, so, going back to the graph paper. Well, if I'm here, I'll just say it like this. If my visual attention is here, then my visual attention on the next step will either be here, or here, or here, and nowhere else. So we're kind of mechanizing, we're kind of mechanizing this thought process, right? We started with a very kind of fluid idea of a human being at a page, and we're sort of turning this into a robot. Uh, what else? Let's see. Now we need to talk about states of mind, right? So we had the three fundamental components of our model for human thought was mind, pen, and paper, right? So uh, we've talked a little bit about where our eyes are, but states of mind, we're going to assume that they're finite. So number of states of mind, number of possible states of mind is finite. It's going to vary from Turing machine to Turing machine, but it's finite. It's kind of a resource. Um, and also one state of mind at a time. So basically, in other words, and it's going to vary from Turing machine to Turing machine. I can divide when my Turing machine is going to involve, for the situation, it can involve however many states I want, but it has to be a finite number. And so typically we're going to use Q equals Q1, Q0, Q1, Q2, dot dot dot, Qn. This is our set of states. The number of states in a Turing machine is usually the part that gets people conceptually mixed up the most, in my experience. Um, but maybe to help you think about it, um, and this is something I thought about pretty recently myself. What does it mean to have more states? Suppose that my brain does like something regularly. Suppose I need to like add numbers in my head, right? That's a computation. We can think about this. Um, what happens when I give a Turing machine lots and lots of states? If a Turing machine has tons and tons of states to work with, uh, if you have lots of different states to work with, then that sort of indicates how smart you are in a limited kind of restricted sense. The size of Q is in some sense a measure of intelligence because think about it like this: the more states that you have, um, the more things you can do in your head without, if I have like, suppose if I have a state in my head for every like possible addition of two numbers that's only a single digit, then I can do those in my head without actually doing any work on the paper. So, and the idea is that the more states you have, the less work you have to do on your paper. In other words, the more things you can do in your head. So, if you're talking to somebody that can, uh, take square roots of large numbers in their head really fast, or do any of those mechanical nerd things that are impressive to people, you can sort of model that in our model by saying he has a lot of states. The number of states of mind that he can cycle through is a big amount. Um, so maybe we'll talk more about that in the future, but we're going to assume the number of states, no matter what, is always going to be finite. What else? And we have to talk about what symbols are allowed to be on the page. Number of possible symbols that can be written is finite. And so at this point, we're sort of talking about the language that he's using to write on the page. Or to be a little more precise, um, we're talking about the alphabet. I guess I'm sort of out of space. I have to move the set of symbols. This is a capital sigma, and we call it an alphabet. This is sort of, yeah. So I mean, sometimes, the typical alphabet that you use is a combination of like, uh, the English alphabet, Greek letters, digits, but it's a finite set. ASCII, And this is going to vary from Turing machine to Turing machine too, but what we'll show is that it doesn't really matter in the same sense that the number of rows doesn't matter. It doesn't really change anything. We'll show that we will show that there's a minimal number of states that you need, or number of symbols. The minimum number of symbols that are needed for every Turing machine for a model of Turing machines that can do everything is two. You always need at least two symbols. That's the simplest kind of Turing machine. Um, and anything else? Okay, one more thing. In a single step, what can happen? So let's look back up here. So in a single step, what am I allowed to do in terms of writing things down? Well, what I'm going to be allowed to do is only the cell that's being looked at will be allowed to be edited. In a single step, only allowed to edit. So I mean, yeah, this is going to be the external response. So the external response is going to be limited to a single to only being able to edit the chain. I'm only allowed to edit the symbol that I'm staring directly at. So in a single step, only allowed to change the symbol in the cell where visual attention is focused. So again, my state of mind is going to change, although it's finite, but the state of mind can be anything. Yeah, so maybe I'll add a second thing. State of mind. Any state can change. States can change into whatever other states. I'll just say states can change however. And I think that's all of the assumptions that we need towards like mechanizing. So let's go over them. So we started out with this fluid process where I'm staring at a page. I'm staring at a particular place. I'm thinking about something in particular. And then based on those two things, what I'm seeing, not where I'm looking, but what I'm seeing, and also based on what's in my head is what is going to change, as well as the symbol that I'm looking at on the page. And it's only one symbol at a time. That's part of the mechanization process. And then we mechanize this by saying, okay, the paper is graph paper. The paper extends infinitely left and right, but usually only one row. Uh, um, our visual attention is going to be focused on one cell of the paper at a time, and obviously one cell of the paper can only have one symbol. The number of symbols is finite. The number of states of mind is also finite, but can be as big as we want it to be. And in a single step, the internal response is going to be a change from one of these Qs to some other Q, one of these states to some other state. Doesn't really matter which one. I can go from Q1 to Q5 or whatever. And I'm allowed to change the symbol that I'm looking at into any other symbol, including the symbol I had before. That would be basically doing nothing. Or I could erase it. We're going to have a symbol for a blank. Um, but I can only change that one cell, and then my visual attention is going to refocus elsewhere, but it can only refocus to an adjacent cell. So through all of that, we've made a large step towards mathematizing this model for human thought and human processing, I suppose. Um, all right, so now that we've sort of mechanized the idea, we've started with an informal idea for a model, and then we sort of mechanize that model, and then we now know enough about what we want to do that we're sort of ready to finally write down a full-on mathematical definition of a Turing machine. So a Turing machine is a kind of object. What kind of object is it is going to be characterized by three things. Um, Turing machines, whoa, this is a little thick. Let me So Turing machines involve three sets, involve two sets and a function. So on the one hand, you have sigma, that's the worst, sigma, the alphabet, the set of symbols, which will usually be standardized. Standard alphabet is this. The standard alphabet is going to involve 0 and 1, but then it's also going to involve this guy, this triangle thing, which looks like a play button, and also this, I'll use like a square U. This thing is going to be known as a start symbol, and this is a blank. And the idea is that we're not going to have a page in like the definition anywhere. We're instead going to have um, the page is in our imagination. And so if the page is in our imagination, then I need a symbol to represent that the cell is blank. So this right here, if I have the U symbol somewhere, then the interpretation is that that's a blank. So I need a symbol to say that I have a blank cell. I also want at least two numbers to be two symbols that I can print on the cell. And then the start symbol basically indicates where my cursor is, where my focus is. So so blanks represent blanks, and then a start symbol represents where attention is focused in the beginning of the computation. So that's the purpose of these two special symbols. And in reality, like I said, the minimal size of an alphabet is two symbols. Um, so in like the most primal form, a Turing machine really just has a two symbol alphabet, 0 and 1 binary. These things are here for our convenience. But this is kind of in terms of when I'm proving things about Turing machines, this is the alphabet I'm usually going to be using. But when you're doing Turing machines, and I will assign you a few exercises in terms of make Turing machines to do specific things, you can make the alphabet whatever you want. If your alphabet, if you're trying to do something with numbers, with like, numbers, then you can make your alphabet equal, 0 through 9, right? That would be your alphabet. If you're trying to do something with numbers, then this would be your alphabet. If you're trying to do something with numbers and you want to write out expressions for some reason, like add a plus sign, you do you. It can be whatever you want it to be. And sometimes when I will do some examples, and for those examples, I will use whatever alphabet is convenient. But I'm also going to prove to you that the alphabet is arbitrary, so that we can switch around. But this will be the most common one that we use. I'll use a two symbol alphabet, I think, for exactly one proof, but it's a pretty important proof. Um, Also, we've got that set of states. And it's also important to note, Turing machines have two sets and a function. This thing is going to be fixed for all Turing machines. In our heads, there's going to be a standard model of computation, and that standard model of computation involves a fixed alphabet. But then there's tons of Turing machines past that, and this is going to be something that does fluctuate. There's no standard for the set of states. You have as many states as you need, but it's important to note that it is sort of a resource. The more states that your Turing machine uses, the more complicated your Turing machine fundamentally is. Um, so that's that. And then finally, we have the function that tells us this. So in general, at any one point, I'm going to be looking somewhere. So I'm going to be seeing some symbol. Let's call it sigma. And then I'm going to note attention by having like a triangle underneath. So this is what at any one moment, this is what a snapshot of the Turing machine looks like. It's going to have stuff. Who cares? I'm not looking at the stuff. I'm looking at a specific place. I'm in some specific state Q. So at any time, At any moment in time, looking at sigma, looking at the symbol sigma, and then in state q. So I have these two symbols, sigma and q, that dictate kind of everything that's going to happen is going to be dependent on these two symbols. And so what's going to happen is there's got to be a function, there's got to be an instruction telling me what to do. And we already know what's going to happen. I already kind of specified it. Um, wait, I want to match the 1, 2, 3. So what's going to happen is that, first of all, this is going to move either left or right or not at all. Let's just say it moves for the sake of argument. It's going to move here. So my visual attention will change, but only to one adjacent cell. Oh my God. It's going to change into a new Q, so the state of mind will change. So it'll change from Q to Q prime, and then it'll change, and then this symbol here will have changed into like a new symbol, sigma prime. And then I'll be focused on a new symbol on the next step. And so there's got to be a function. There's got to be a function that has all the information I need in order to do this step. I'm going to call that function delta. And delta is the transition function. The transition function of a Turing machine is basically the program. It tells you what to do given that you're in a specific state of mind, Q, and looking at a specific symbol, sigma. And what it does, in the case of the picture I just drew here, it's a function. It's a function which takes as an input takes the pair sigma q, and as output returns three things. It returns three things. It returns, first of all, a new symbol that I want to replace the old one with, a replacement symbol. It returns a new mental state that I'm supposed to go into. And finally, it has to return a direction. And the direction is only going to be one of three things. And those three things, if it moves right, I'm going to say negative. I'm going to say if it moves left, so D is an element of -1, 0, 1, where -1 implies move left, 1 implies move right, and then 0 implies, of course, don't move. And this is an optional one. You don't lose any. Your Turing machine doesn't lose anything with a don't move option. So just kind of like the start symbol and the blank symbol were arbitrary. I mean, we're not arbitrary, but they're for convenience and not actually super necessary. The 0 option, the option for not moving, is also something that's just there for our convenience. Really, you just need to move left or move right option. But that's what the transition function fundamentally is. So you've got three characteristic kind of objects that together constitute theoretically a Turing machine: the alphabet, the set of states, and the transition function. Um, and the transition function, just to kind of um, if you're familiar with Cartesian products of sets, delta is a function that takes the product sigma cross q to the product sigma cross q cross -1, 0, 1. So that's fundamentally the kind of object that delta is, the transition function. It's a function that takes a pair. It takes a symbol and it takes a state, and as output it returns a new symbol, a new state, and a direction to move. So that's the idea. Now we're going, and that's the syntax of a Turing machine. That's just the syntax. We still have to define the semantics, but let me summarize in a full-on definition what I just did, what I just said. So, definition. When I write DEFN here, it means definition. A Turing machine which I'm going to often abbreviate TM, is a triplet of objects. It's a triplet. It's a pair. It's like a pair, but it's three things. It's a set sigma. It's an alphabet, a set of states, and a transition function. Where sigma is a finite alphabet. Q is a finite set of states, and delta is a mapping. It's a function that takes sigma cross Q to sigma cross Q cross -1, 0, 1. There's a few extra things I want to say about what a Turing machine is, kind of as a syntactical mathematical object. We're going to require Q equals Q0, Q1, dot, 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 Qn, so n things in it. We're going to always kind of imply that Q0 has some special meaning. Q0 will be called and sometimes I won't use Q0. Sometimes I'll use like QI if it's more convenient to use Q0 for something. Q0, the first one, there's a special, let's say this. In Q, we always have a special symbol, a special state, QI, which is the initial state. So this is going to be kind of the standard starting state. Usually Q0. And it's actually special states plural, because we're also going to have and QH, which is the halting state. Now we're going to have a halting state QH, and usually that'll be the last state. But sometimes, like I said before, we're usually going to be interested in decision problems, right? Problems where the Turing machine is supposed to return a yes or a no. And to indicate yes or no semantically, we could have it be the case that the Turing machine just erases everything and puts a 1 there and stops and halts and goes into the state QH. That would be one way to return a yes answer and a 0 for a no answer. But to make our lives easier, a lot of the time, instead of QH, we'll have QY and QN, which will for accepting and rejecting, respectively. So Q yes will be like an accepting state, Q no will be a halting state for yes and no, respectively. And sometimes it'll be convenient, to interpret the QY answer as an accepting state rather than program in, delete everything, and replace it with a 1. Again, that's just for convenience, but that'll be the interpretation. Sometimes we'll have 1 state for halting, and sometimes we'll have 2, depending on what we're doing with our Turing machine. Also, sigma we'll usually have, you know, the play symbol and the blank symbol. The bottom line is that there's just like queues, will kind of cheat sometimes in terms of what's going to be interpreted as the blank and what's going to be interpreted as the play symbol. And technically, these are all you need. All you really need is a play symbol and a blank symbol, because the blank can function also as just kind of arbitrary content somewhere. You can print blanks wherever you can print these start symbols wherever you want, and I define what those are. So that's the syntax. So this defines the syntax of a Turing machine. Now we need to define the semantics of a Turing machine. How do I interpret what a Turing machine does? What I really need to do now is I want to define this picture I drew up here. I want to mathematize this picture right here. This is a configuration. You can see it at any one step. What I'm going to have is I'm going to have a set of tape cells that have some content on them, and then I'm going to be in a state, and I'm going to be looking at a symbol. And so I want basically a mathematical object called a configuration that represents all of this information together at once. So I'm going to define configurations, and then I'm going to define what a step means, what a step of the Turing machine means out of that configuration. So what does it mean for one configuration? What does it mean for a step to happen? Is going to be basically to say like that this one configuration C yields this new configuration C prime in one step. So the configurations are a step towards defining what I mean by the word step. So that's the next thing I'm going to define. And you kind of just have to see all, I mean, the first time you see all this defined, it's kind of overwhelming. You'll probably have to go through it twice and see some examples with me. And I will do examples for you to really see how all of this comes together and models the thought process that we had. So a configuration is the next thing we want to do. Oh yeah, and I forgot to mention delta is the transition function, but whatever. So a configuration. And a configuration we're also going to sort of cheat. It's really, really hard to standardize computability theory in like one collection of definitions. It's sort of, no matter what you do, you're always going to encounter one proof where you sort of wish that you defined something a little bit differently, but it doesn't really change much because fundamentally what a configuration is, underline my definitions, fundamentally what a configuration is just a complete description of the Turing machine at any one step. It's the formalization of that picture I drew with the tape and the stuff. So a configuration is a triplet, just like the Turing machine. It's a triplet of objects, but they're different objects. I'm going to use like a lowercase c to denote it. T, Q, Z. So what are these things? T is a finite string. Oh no, I should have probably defined what a string is first. Dang. I'll just say collection of symbols, or uh, sequence of characters. Sequence of characters. That's what a string is. So if I have a bunch of characters in my alphabet, if sigma is equal to A, B, C, then a string in the alphabet sigma would be, A, B, C, E. That's a string. A, that's another string. B, C, that's a string. That's what I mean by string. Whoops. So what T is going to stand for, the letter T stands for tape configuration. Eraser's kind of laggy. T is a finite string called a tape configuration. Which represents what's on the tape. So keep in mind we have a starting step. So at any point in time, the Turing machine is on, say, step 20, step 30, but the number is finite, meaning that the number of non-blank cells on the tape is also finite. So, if I have a tape that looks like this and everything is blank, everything else to the left and the right is blank, then T for the tape configuration would look like this. It would be this string A B C D E. So the tape configuration is a finite string that basically shows me exactly what the tape looks like. It's a finite string, and it can be always assumed to be a finite string, even though the Turing machine is allowed to do infinitely many steps. At any one step, it'll be on a finite number of steps. So it's a finite string that encodes everything of value that's worth looking at on the tape. Initially, the tape will be all empty except for like your input and that starting symbol, and so we'll talk about that too. But that's what the first thing is. So the T in this configuration C represents the contents of the tape, the contents of the page, what's on the page. Q is of course the state. Q is a state. I'll just say Q is in Q. It is a state. And Z is an integer. By the way, the integers are, it's all of the numbers, -3, -2, -1, 0, 1, 2, dot, 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 right? So that's the integers. Again, if you're not familiar with set theory or anything like that, you should check the video description for a PDF that runs you through these basics. Is an integer. And what does this integer represent? Well, I have the tape contents. I have the state that I'm in. I also need to know where the cursor is. Where am my visual attention? Indicating intuitively represents where attention is. And I'm going to start calling the visual attention area, the visual attention foci, the index. So that's sort of a pseudo vocab word. So intuitively it represents where the attention is. I can get away with an integer as an indication of that because remember, I only have one row of my graph paper. And since the idea is that I'm going to start somewhere, I'm going to start where the play button is. The play button tells me where I'm going to start. I can just declare this to be z equals 0. So that the cell, 3 cells over here, this is z equals 3. And then I can say over here, this is z equals -2, right? So these three things together, the tape contents, the tape configuration, the state, and the indication of where my focus is, if you think about it, that does give you everything that you need to know about what the Turing machine is doing at any one particular moment in time. And I might, at some point, for some proof in some future time, I might conveniently pretend that I define configuration slightly differently. But as long as the configuration does encode these three things, there's a one-to-one correspondence between the definitions, and it still kind of works out. All I really need with a configuration is a complete description of the Turing machine, which includes what's on the tape, the state I'm in, and where my attention is. So this is the way I'm going to do it right now as a triplet. By the way, for any z, it doesn't have to be this one. Maybe I'll say for any like n, let t of z, I'm going to put these brackets. If I write t of n like this, is the symbol at index n. So, so for example, if t is equal to 3a 4 plus negative, let me divide sign this, then t of, I'll call this 0. Actually, I'll call this 1. Then t of 3 will equal 4, right? It's the third thing. So this is just going to be my way of talking about specific symbols on this tape configuration. That's the idea. So that's configuration. Now, finally, we're going to define the all-important yields relation. So now we're going to talk about what a step kind of looks like in the abstract. Okay, so here's kind of a third definition that involves Turing machines. So let M equal sigma q delta be a Turing machine, and let and C1 and C2 be configurations of M. So you got these two arbitrary configurations, and what I want to define is what it means for this configuration to yield this configuration in one step. So we say that C1 yields C2 in one step. And write C1, C2, and we put an M here. This is the notation to say C1 yields C2 in one step. If, and before I just write down what it means, let's figure out what it should mean. So what should it mean to yield a configuration in one step? Well, here's a configuration. Here's what it represents visually. I should probably actually define, crap. Let me do this. I want to give C1 equal, I want to make it equal to something. So C1 is going to equal, let's just say T1, Q1, Z1, and C2 is equal to T2, Q2, Z2. There we go. So what does this configuration look like? Oops, no. So this so C looks like this. I need to make that bigger. I'll use this. So here's C1. And my cursor, let's say, is right here. I'm in state Q1, and I'm in, what is this here? Well, T1 is all of the tape contents. So what's in this symbol right here, the symbol in this cell is actually T of Z1. So this is what configuration C1 looks like. I mean, if you look at the whole thing, you'll see T1, but in one step, this is what I'm looking at. And so what would it mean for this to yield this? Well, it would look like this. So how did I say this? So first of all, how are these integers related? So this is Z1 as an index. What does Z2 have to be? And if C1 is to yield C2 in one step, well then Z2 would have to either be this, or this, or this. It can only be one of these three things. And either way, no matter what it is, it's D. It's Z1 plus D. If Z2 equals Z1 plus D, where, delta of T1 of Z1 Q, crap, I'm out of space. Where delta of T1 of Z1. So I have, obviously I have this transition function. I have a symbol that I'm looking at, and I'm in a state. And so the transition function is going to take the symbol that I'm looking at and the state Q1 and spit out three things. Remember, uh, it's going to be a new symbol, sigma 2. Um, well, I'll leave that empty for now, but it's also going to give me a new thing, Q2. Well, okay. I mean, what does delta have to be? Whatever D is here, that's the D that's right here. So it's going to have to be D. So Z2 has to be Z1 plus D, where D is the thing that's spit out by delta. It's the third argument given by the delta. And then also this, I'm going to replace this Y with an AND. And delta of T1, Z1, Q1, T1 of Z1, comma Q1 has to equal, the next symbol has to be whatever T2 of Z1 is. That has to be what's there in the next state. So this has to be T2 of Z1. And then Q2 has to be the state that it outputs. And then D is the direction, where Z2 equals Z1 plus T. I probably should have said this first and then this second, but these are the two conditions. Z2 equals Z1 plus D, and then this is the relation that has to be true. So this is what it means for C1 to yield C2 in one step. It's just a formalization of the transitions between configurations that we're kind of envisioning. It's very formal, and we might not use the formality a lot or all the time, but it is important that we do formalize it so that we can have the option of um, talking about it this formally in order to prove things that are rigorous. So we won't always use this, but it's important to go through the process of formalizing it just once. So that's what it means for C1 to yield C2 in one step. And then inductively, we can extend this definition to what it means for C1. We can now define what it means for it to be yielded in many steps. We can define C1 yielding C2 in k steps for some k in the obvious way. So I'm not going to go through all of that, but basically now for this, if C1 yields C2 in k steps for some k, we're going to write C1 arrow C2, and we'll put an M here, but then we'll put a K as like the power to imply kind of that the machine, the yields relation is just kind of being used. You know, we're kind of just doing K steps. We're doing the M. M is happening K times is essentially what the notation is there for. So that's the yields relation. So, I mean, you can see how we're kind of defining semantics now. We define the Turing machine in terms of like just a collection of three things, two sets and a transition function. But also, you know, we've also got this yields relation. Now we're sort of talking about what a step formally means and what a configuration formally means and stuff. So this is what I mean by semantics. Now we need to define starting and stopping and halting and stuff like that, and how to interpret that stuff. So first off, we want to talk about inputs. So I mentioned that sigma always has a blank symbol. We're going to require that inputs don't involve any blanks, except when we're modeling functions that take more than one input. In that case, we'll split up the inputs by blanks. So for strings, you know, x, which don't have blanks, we'll call these inputs. call them inputs. And then for any x, we want to define an initial need an initial whoops need an initial configuration for x. So that's what we're going to define next. And so that'll just be kind of what we need it to be. So t of x is how I'm going to denote that. And that'll be defined to equal, this is what, the colon equals is a definition. It means I'm defining t of x for any input x to be what? It's going to be, wait, I'm sorry, getting ahead of myself. Cx, that's what's going to denote the initial configuration. And that's going to consist of t sub x, and I'll define what that is in a minute, q sub I, whatever the initial state is that's guaranteed to be there, and also 0, where z is 0. Remember, a configuration consists of a string that represents the tape contents, a state, which I want to be the initial state, obviously, and also 0, and to indicate that the location that I'm starting at is the 0 location, and then everything else is relative to there. Where t sub x is equal to effectively just the play symbol followed by x. So to kind of be more formal, t of 1, I'm not going to be more formal than that. You get what I mean, right? The initial configuration represents this. I'll be more formal with strings and stuff in a little bit, but I think hopefully people get the idea. Actually, I don't want all those. So initially, we have a situation like this, where we have the place symbol, where we're pointed at the place symbol, we're at index 0, or we're just going to declare that starting point index 0, and then x is just kind of as much as it needs to be. And we're in state qi. So when the Turing machine starts up, this is how it's going to look. We're in the initial state, we're pointed at the place symbol, x is going to follow the place symbol, it's some finite string, and then everything is blanks following that. And so this, c sub x represents this. This is our initial configuration. So now that we have an initial configuration, we also have defined now we can start to think about the Turing machine doing things, because we take the initial configuration for an input, and then we just use the yields relation repeatedly on it, and then we get results. And now we've sort of semantically modeled the steps. Okay? So now we need to define what it means for a Turing machine to halt. So we say that M halts on input X in K steps if, I'm going to define state. So if K is for some K, if, okay, we say M halts on input X in K steps if this is true. If C X yields, I cannot draw my arrows without going up, there we go. In K steps, C sub X yields some new configuration C, I'll call it CH, where CH equals this. It equals T for some T we don't really care about, but more importantly, Q has to be the halting state. For some T and Z. We don't care what T and Z are. What we care is that at some point, for some number of steps, eventually, the initial configuration yields a halting configuration, in the sense that at some point, the state here will be the final state, to indicate that my mental state has detected I am at the end and I'm finished. So to be to halt on an input is to say that eventually, for some number of steps, we get to a halting state. And the interpretation of getting to a halting state is that the Turing machine stops computing. There's no more computing to happen. Um, if we're talking about accepting and rejecting, if we have q y and q n instead, then we say m accepts the input x if ch equals t q y z, and m rejects the input x if ch equals t q n z. So sometimes we're concerned with accepting and rejecting, and again, this is just there for convenience. We could easily, instead of doing accepting and rejecting, we could just erase everything. Once we could use just one halting state by saying, okay, um, you've halted, you have an answer, supposedly just erase everything, print a one, and then stop. But then that leaves one last thing to define, which is the output. Um, also define, also if m halts in k steps, in some number of steps, in configuration, t, q, h, z, we call the string t the output of the machine. So the string that we're left at when we halt, if we halt, is the output of m on input x, which we denote m of x. So that's the output. So sometimes we're concerned with accepting or rejecting, in which case we don't really care what t is. We just care if we get into a halting state that's yes or no, and then this is just the scratch work we use to get there. And sometimes we are concerned with the output. Sometimes we want to think about m as like computing a number for us, in which case the output will supposedly be that number. And we're going to denote it m of x. Also, however, the machine might never halt. If the machine does not halt, for any k, then we're going to write this for the output. Instead of, I still want to say that m of x equals something. Then instead, I'm going to write m of x equals diagonal arrow. So the machine output will always, I can always say m of x equals something. If it halts, then it's going to equal whatever the tape configuration was at the time that it halted. And if it doesn't halt, it equals this arrow to indicate that it does not halt. It's just notation for me to tell me something. So you can sort of think of the Turing machine as a function that takes inputs and spits out outputs. And in this way, it sort of double functions as a function. It models a function, right? It only really models a real function if it always returns an output. In other words, m of x, the Turing machine only really represents a function if this never happens. So that's that. So that's a Turing machine. That's the whole definition of a Turing machine. I know it's extremely, that's probably the most complicated math definition that most people have seen before. Let's zoom out and see how much we just did. Whoops. Yeah, all of this is one definition, really, starting, well, I guess starting here. This is all one definition. uh, and we're sort of not done yet, because what I want to do now is I want to define what a problem is, and I want to define what it means to solve, for a Turing machine to decide a problem, to solve a full-on problem. I have what it means to accept and reject inputs, but now I want to talk about problems themselves being computable. So let's do that next. I'll do that on the side here. So next we want to formalize decision problems and say what we mean by a Turing machine solving it or deciding it. Okay, so let's formalize what we mean by decision problem. Well, a decision problem, recall from the last video, is a problem that it's a problem where the answer is yes or no. So an example of a decision problem would be, factoring, the factoring problem. That's going to be an important one. Right? So factoring, it is the problem given an integer z, does it have a fact? Does it have a non-trivial factor? Um, that's the question. So if I gave you a 4, the answer is yes, it has 2. If I gave you a 7, the answer is no. That's the factoring problem. It's a decision problem. Does the number have a non-trivial factor? Yes or no? Um, that's informally what the factoring problem is. So it's another example of a problem. About add. This is a stupid problem. It's sort of the addition problem. It's sort of the decision problem version of addition. Given 3 integers, A, B, C, is it the case that A plus B equals C? Right? So that's sort of the yes or no problem version of addition. So these are decision problems. I'm stating them informally, and what we want to do is kind of view them as objects. But how do I do that? How do I view them as objects? So this is the informal kind of thinking about a decision problem, and we can formalize this by uh, looking at a decision problem as a collection, as the collection, as the set of all yes answers. That's how we view it. So in other words, it's a set of strings. A decision problem is a set of strings where the interpretation of the decision problem is that that the answer is yes if you're in the set, and the answer is no if you're not in the set. So formally, the factoring problem is the set of all of the yes answers. So the first one would be 4. 1 and 2 and 3 are prime, or yeah, 1 is prime, I guess. 6, 7, 8, 9, 10, 12, 14, 15, 16, 18, and so forth. This is the factoring problem um, as a set. So it's a set. Now, it's a set of numbers, but remember, when I was talking about Turing machines, I was talking about strings. So this is the formal way to define the factoring problem. But let's talk about kind of more generally, formally defining a decision problem in general. What kinds of objects are decision problems? So again, recall we have a finite alphabet, sigma, Doesn't matter really what it is. In the case of, and so, what I'm going to define here is define sigma star to be the collection of all finite strings of characters from sigma. This is an operation that you can do to an alphabet. So I take an alphabet, which is a finite set of characters, and I can kind of apply the star operator to it. And what I get is this infinite set. It's infinite regardless of how many things are in the alphabet. It's the set of all finite strings. Sometimes the star is called the Kleene star operator. That doesn't really matter. But so this is the set of all finite strings. And so for the factoring problem, what is sigma? Sigma for the factoring problem is the set of digits. It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a 10-symbol alphabet for the factoring problem. That's kind of the natural alphabet for it. And so you can kind of think of all these numbers. It's going to get into 3 digits, 4 digits, 5 digits. They are numbers, but we're really more thinking about them as strings. Really more thinking about them as collections of characters over an alphabet. And so what the factoring problem is, whoops, I don't want to erase this yet. So what is the factoring problem then as an object? What it is factoring, it's a subset, right? The factoring problem is a subset of this sigma star for this particular alphabet sigma. It's a subset of sigma star. And that's how we're going to define a decision problem in the abstract. So here's my definition. A decision problem otherwise known as a language. I'll talk about why that is in a bit. Is any subset L contained in sigma star. That's what a decision problem is. A decision problem is a set. It's a set of strings over an alphabet, where the interpretation is that the decision problem is always intuitively the decision is X in L. X is the input, and the machine is supposed to give me a yes if it is in the set and a no if it's not in the set. So the factoring problem here, I give it a random integer, and I can sort of frame every decision problem in the exact same way. Not only is it a yes or no answer, but now I can always kind of say that it's not only the same answer, but it's the same question. The question is just, are you in the set or aren't you? That's the question. And so a decision problem is the set of all the yes answers. It's the subset of the alphabet. And so this is what a decision problem means in the abstract. And now we can finally define what it means for a Turing machine to compute a decision problem. Okay, so let L, okay, why is this a language, by the way? Why is the other word for decision problem a language? I am going to use the word language a lot by accident. It's because there's this very deep connection between computability theory and actually formal linguistics, in the sense that how did I get, there's a way to build languages out of an alphabet. If instead of thinking about an alphabet, don't think of it as an alphabet, but necessarily, in order to understand why it's called language, instead of thinking about alphabets, think about like these symbols as sort of like words in a language. And then I could specify, what I could do is I could create a grammar. I could like define rules for how to put these things together. Like what does sentence structure look like and stuff like that. I can define a set of rules called a grammar. And then out of that grammar, you do get a set of all valid things. You get a decision problem. And so the decision problem in that context of linguistics is this a valid sentence in the language? Or is this a valid sentence? Yeah. So that's why you call these languages. It's kind of, you start with a set of words or symbols, and then you define a grammar, and then that creates for you a decision problem. And there's a deep connection between categories of machines and languages. But that's not something I'm going to get into anytime soon. Because it's less syllables, I think people like to say the word language instead of decision problem, and I am one of those people. So I will say the word language quite a bit. When I say language, I mean decision problem. It's kind of weird, but it is what it is. In a lot of textbooks, they use languages too. So let L be a language or a decision problem. Let L be a language, and then M be a Turing machine. We say that M decides L. Oops. Other words. There's a lot of words for this because this is the definition. We say that M decides L, but otherwise, instead of decides, I could have used the word computes. I could say the word solves. I could say the word um, uh, uh, decidable, computable. I could say, well, yeah, that's pretty much the only two other ones. So M decides L, M computes L, M solves L. We're defining what it means to actually solve a problem in general. If the following is true, two things have to be said. One, if X is in L, well, let me just go ahead and say it like this. If X is in L, then what should happen? Well, then M should accept it in some number of steps. So, so if X is in L, then M accepts X in K steps for some K. And then if X is not in L, then M rejects X in K steps for some K. That's what I mean. This is the definition of deciding a language. If you're in the set, then M accepts the input, and if you're not in the set, then it rejects it. That's the definition. So there's a thing I want to say about that, but before I do, we're almost done. I know this is going very long, but this is the hardest part. This initial definition is probably going to be the hardest part of any of my videos that I'm going to make. Um, in terms of just there's a lot to digest here. You're going to have to go through this a few times and really kind of categorize it, I guess. Um, so now we want to talk about the problems. We say that a language L is decidable. Or computable or solvable or whatever. And there's actually one other word that we use for it, or recursive. That's another word for it. All of these are words for the same thing, to say that L is computable. Computable, solvable, recursive, decidable, these are all going to mean the same thing. L is decidable if there exists a Turing machine that decides it. That's what it means. So we finally did it. It took, I don't know how long, but we finally we finally formalized what we've been talking about. We have what a decision problem means. We have what it means for a decision problem to be computable. We defined our Turing machine model formally, and now we know exactly what it means to say that a language is computable. Um, I know that was a lot. I know that was a lot to absorb in one video. But what we're going to do in the next couple of videos is we're going to do a lot of examples. We're going to do examples I'm going to show you. We're going to go through the process of designing Turing machines that compute problems, and we're going to think about them, and you'll get used to them through that. But I do recommend before moving on to those videos that you look through this definition closely, that you maybe write it down yourself, and that you think about it. And if you have any questions about it, please ask me in the comments. A couple last things I want to point out. One, why did I have to say two different things here? Why wouldn't it have? Why isn't it enough to just say? Whoops. Why can't I write instead of these two separate points? Why can't I just write one point? Why can't I just say x is an L if and only if m accepts x in k steps for some k? Why can't I do that? Why don't you think about that? In fact, actually, I don't want to tell you the answer. I mean, this should be something that you should be able to figure out the answer to. I'll tell you in the next video what the answer is to this. Why does the definition of deciding a language have to involve two different points, where x is an L means m accepts, and where x is not an L means m rejects? Why isn't this good enough? Why can't I just make it a two-way street with the positive, where x is an L means m accepts? Think about that. And then another thing to do is one last definition, really important definition. We're going to come up with our first category of problems. So we call the set of all recursive or computable problems or languages. Again, problems and languages are kind of the same. They are used interchangeably. R. That's what we're going to define it as. The set of all languages that have Turing machines that compute them is denoted R. This is our first complexity class, or computability. This is our first class of problems. And then sometimes also sigma star is referred to as all languages, because that's what it is, right? It's just the set of all languages. Well, actually, no, it's not actually. I'm sorry. The power set of that is all. And if you don't know what power set is, again, check my set theory notes. But we can finally draw the landscape. What you're going to see is that this class sort of turns into a zoology class, where our job is to categorize things. So we have a fixed alphabet, and then we have kind of two big classes. We have all languages, and then we have the recursive languages, R. And so you might be questioning, what is the difference between these two things? The fact that I drew it this way implies that there does exist a language that is not recursive. And there's plenty, most of them, in fact. And so we'll talk about that very soon. We'll define a language that is not recursive, that there is not, we'll talk about problems that are not computable. But most of our time is going to be spent inside of R. In fact, inside of a special class called Re. But the beginning of our zoology project has happened at this point. We've defined the two biggest kind of complexity classes. Not really biggest, but anyway, next time we will do examples. We will make Turing machines that solve problems for us. So look through what I just told you, and I'll see you then.